All right. So again, chapter 5 is gases. Hopefully you got into this at the beginning of the week. I want to just go over some of the basics with us. So pressure, when we talk about pressure, we're talking about force over area. For gases, when we talk about gases, we're talking about the force of those individual particles, gas particles, colliding with the wall of whatever container we're in, right? And so the force of those individual collisions divided by the area, the interior area of that container, that gives us the pressure for a gas in terms of chemistry. But we think about it lots of different ways. The air in your tire, right? That's the pressure, the force of the collisions of that air that's in your tire colliding with the walls of your tire. Atmospheric pressure is the weight of all of that column of air above the earth pressing down on ground level. And so another way we can think about this is well, not equal to, but related to collisions. We'll get a little bit more into that when we talk about kinetic molecular theory here in a couple of minutes. The units for pressure, the SI unit is the Pascal. And that's 1 Newton per meter squared. So that's the standard SI unit for force, Newton per meter squared. And this is a really tiny value, right? 1 atmosphere is more common, right? And so that's supposed to be the pressure at sea level. And 1 atmosphere is 101 kilopascals. Right? So a single Pascal, not a lot of pressure, but atmospheric pressure is 101 kilopascals. Another way that we can think about an atmosphere is in millimeters of mercury. And so 760 millimeters of mercury. And that's a very old-fashioned way of thinking about it. Mercury is a very dense liquid, right, at room temperature. It's the only metal that's a liquid at room temperature, and it's a very, very dense material. And so they made barometers out of mercury. They still make barometers out of mercury sometimes, but a lot of it's electronic these days. And the way it would work is that, you know, if the atmospheric pressure matched the pressure inside the barometer, then they would be even, right? And so there'd be no difference. And then if the pressure outside pushed down on the mercury because of the increase in pressure, it would make the difference in the mercury level a certain amount. And so if we have vacuum on one side of the barometer, atmospheric pressure pushing down on vacuum made that height difference 760 millimeters. And so it pushed the mercury up by 760 millimeters, and that was 1 atmosphere. And so that's kind of an outdated unit. They have modernized that unit by calling it a torr, and it has exactly the same size. And so 1 torr is 1 over 760 atmospheres. So again, these are kind of small units, but they're good for dealing with low pressure. Here in the US, if you look up a barometric pressure, it's going to be about 30 inches of mercury, right? Because we don't use the SI system, 760 millimeters is about, I think it's 31.5 or something inches of mercury. And so you might see that if you watch the news and listen to the weather report or look up a pressure online. And so we have lots of conversion factors here to go from atmospheres to torr, atmospheres to millimeters of mercury, atmospheres to pascals. So just be able to use those. The ideal gas equation, I think most folks got that down pat. It's a pretty common one to see even before you get to a college level class. PV equals nRT. I'm going to start with this R. This is a gas constant. And so it's always the same. 0.0821 liters atmospheres per mole Kelvin. And so that gas constant tells us what all those other variables need to have for their units. And so to use the ideal gas law, this pressure must be an atmosphere. Our volume must be in liters. The amount of our substance must be in moles. And then, of course, our temperature has to be in Kelvin. Remember our conversion, Kelvin is equal to the degree C plus 273. We can't have negative pressures or negative number of moles or negative volume. And so that's why we have to use a Kelvin scale because there are no negative values for temperature when we talk about Kelvin. There is a Fahrenheit equivalent of Kelvin called the Rankine scale, but we don't really use that a whole lot.
Dr. Davis.
Yes.
I remember for part of the Alex, instead of for the R, we had to use like 8.42 something, I
think. So there is, if we change these units to from liters atmospheres to joules, we get 8.314 joules per mole Kelvin. Right? We will see that in chapter 6. It's the same constant, it just has different units, right? We convert those liter atmospheres into joules. And this is when we are more interested in energy than we are in volume and pressure, right? And so we'll see this value in chapter 6. Is that what you were talking about, Michael?
Yes, sir.
Yeah. So you will have to sort of get pretty good at recognizing when to use which value for R. You're right. Especially next week when we're going to have sort of a mix of chapter 5 and chapter 6. We're going to need both of those R values at different times. And so, don't let that trick you up. If we're interested in energy, we're going to use the one with joules. If we're interested in volume or pressure, we're going to use the one that has liters and atmospheres. Okay. Now we can rearrange this ideal gas law. Because it's all equal to a constant, we can set it up this way. PV over NT equals R. And if this is true for all ideal gases, then if we have one ideal gas, P1V1 over N1T1, it must be true for a second ideal gas, P2V2 over N2T2. Okay? And so this is what's called the combined gas law. We can drop out the R in that case, right? We don't need him anymore because these two have to be equal to each other if they're equal to R. When we use this combined gas law, if anything is constant, then of course it's the same on both sides and it cancels out. So let's say that we don't add or remove any gas particles, right? The number of moles doesn't change. And let's say that we have a very rigid container. It's made out of stainless steel or something. Then our volume is not going to change, right? And so this would be a constant volume and the constant number of moles, right? Then we just get P1 over T1 equals P2 over T2. Right? And so we can use this combined gas law to solve for changing systems, right? Usually we start at one set of conditions, we end at another set of conditions, and we want to see how, say, the volume changed, or the pressure changed, or the temperature changed. Okay. All right. The last thing that I want to do that's sort of a review from last time is standard temperature and pressure. We call this STP. There are a couple of different definitions. I'm going to use the one from our textbook. And so standard temperature and pressure is 0 degrees C and 1 atmosphere. Okay. So that's 273 Kelvin and 1 atmosphere. We really use this as sort of a shortcut when we're writing a problem. You know, at STP, there's 2.7 grams of a gas. What's its volume or something like that. This image here is if we plug these two values, temperature and 273 Kelvin and 1 atmosphere, if we plug that into the ideal gas law at 1 mole, we plug that in and we get a volume of 22.4 liters. And so that's helpful to us if we're, you know, it saves us a step, sort of. If we know that conversion factor at STP, then it saves us a step of actually plugging it into the ideal gas law, right? Of course, if you don't remember this ratio, by all means, plug it in. It's not going to take you that long, but it's a nice little shortcut. Okay. Partial pressure. So still jumping forward a little bit. I think this was at the tail end of one of those videos. I just wanted to reiterate. The Dalton's law of partial pressures requires these conditions: the volume of our container and the temperature of our gas has to remain constant. If either of those two things changes, then Dalton's law doesn't hold. Right? But Dalton's law tells us that if we add two gases together and we maintain the same volume of our container, we maintain the same temperature, what's going to happen is that the pressure of that mixture is going to be equal to the sum of the pressures of whatever that mixture is made of. Right? And so we call it a partial pressure because P1 is, of course, just part of P total, P2 the other part of P total, but we can separate those out. Even if we don't separate the mixture, we can separate them out mathematically. So if we have these two gases mixed together in our partial pressure problem, we need to solve a couple of things. First off, we need to figure out what the ratio of these two is in terms of moles. And we call that ratio the mole fraction. It has the symbol chi, which is sort of a Greek letter X. And so chi for gas A is equal to the number of moles, remember that's little n, of A, divided by the total number of moles in tote. For gas B, the mole fraction of B is equal to the number of moles of B divided by the total number of moles. And again, just so we're all on the same page, in tote, of course, is the number of moles of A plus the number of moles of B. Right? And so that's our mole fraction, XA. When we're calculating the partial pressure, the pressure of A is just equal to that mole fraction of A times the total pressure. And for B, the partial pressure of B is equal to the mole fraction of B times the total pressure. And again, just so we're all on the same page, the total pressure is equal to the pressure of A plus the pressure of B. That's Dalton's law in a nutshell. And so sort of remembering these two equations, the one for mole fraction and for partial pressure, writing them more generally, the mole fraction for any component I is equal to the number of moles of I divided by the total number of moles, and the partial pressure of I is equal to that mole fraction times the total pressure. Whenever we're given a system and we don't know the individual number of moles of each compound, we can use the ideal gas law, P tote V equals N tote RT, right? We can figure out the total number of moles in a system if we know the pressure of that system. And then we can work backwards to figure out the individual number of moles of each gas. Okay, so let's do a quick example of partial pressure. In this one, we know the number of moles of each gas, neon, argon, and xenon. These are mixed together. The total pressure is 2 atmospheres at a given temperature, right? So at a certain temperature, that tells us that the temperature is constant, right? It's not changing on us. It doesn't tell us that volume is constant, but to use these partial pressures, we know that the volume has to be constant as well. And so the partial pressures, we need to find partial pressure, we need to find these mole fractions. So for neon, we have 4.46 divided by everything. And so 4.46 plus 0.74 plus 2.15 gives us 7.35 moles total. So that's a mole fraction of 0.607. Mole fraction doesn't have a unit. We end up with moles over moles. And so the mole fraction is unitless. And if we add up all of our fractions, we have to come out to 1. So as long as we solve for 2 of these, we can do the third one by subtraction. Right? Argon, 0.74 moles divided by 7.35 moles. That's going to be pretty close to 1.1, 0.101. And so for xenon, we can do the division here, or we can just do subtraction, right? It's going to be 1 minus 1.01, sorry, 1 minus 0.101 minus 0.607, and we get 0.292. To find partial pressure, again for neon, we know the total pressure is 2 atmospheres, so it's just 0.607 times 2 atmospheres. You end up with 1.214 atmospheres, only 3 sig figs, so 1.21. The pressure of argon, 0.101 times 2 atmospheres is 0.202. And again, for xenon, we could calculate it out, or we can just do subtraction. We know they have to be 2 atmospheres total, so we can just subtract that out. 2 minus 1.21 minus 0.202 is 0.588 atmospheres. And so that's partial pressure. As long as we know how to find the mole fraction, we should be pretty comfortable finding those partial pressures. We need to know those 2 equations, the equation for mole fraction and then the equation for partial pressure.
How did you get the last answer again?
Yeah, so for the xenon, we know that there's 2 atmospheres total. And so 2 atmospheres minus 1.21 minus 0.202 should give me 0.588.
Okay, thank you. I got that now.
You could, of course, do the 0.292 times 2, you'd get 0.584. And that's just because we dropped a sig fig here. Close enough. Right, close enough. All right. So moving into this kinetic molecular theory, this is a little bit about what we started talking about in lab yesterday, what you worked through in lab yesterday. And so kinetic, how things move, molecular, well, we're going to talk about molecules. And so this is the theory about how gas molecules move. It has 4 basic pieces, and we're going to go through those here pretty quickly, but we're going to work out some math with those as well. And so first here, any gas is composed of molecules or atoms, right? It could be something like helium, which is just atoms, not molecules, but they're separated each other by very large distances, relatively speaking, right? Even if they're only separated by 0.5 millimeter or something, that's huge, given that the size of a single molecule is on the scale of nanometers, right? And so these gases are separated by huge amounts relative to the size of an individual molecule. Because of that, we consider these to be very point particles. We essentially say that they have very little volume, hardly anything. Right? So negligible volume is the important part of this first point. Okay. Second, gas molecules are constantly moving, right? They move in random directions. They're having collisions all the time. And the second point, kinetic molecular theory treats these collisions as elastic. Who has had physics and knows what an elastic collision means?
It means when they collide, they stick together, right?
Not necessarily stick together.
Dang.
That would actually be an inelastic collision.
Oh, they don't stick together?
Yeah, so they don't stick together, but more importantly, they don't lose any energy, right? If when real things collide, they can heat up, they can lose their energy to friction from colliding with one another. They can lose energy to heat from deformation. They can lose a lot of energy. The kinetic molecular theory assumes that all of these collisions don't lose any energy. This third point says that there are no forces, either attractive or repulsive, between gas molecules, right? So nothing that will attract these two gas particles together. They won't, they're not like magnets. They don't attract one another at all. They don't repel one another. And the last, this is another physicsy thing. The kinetic energy of the molecules is proportional to the temperature of the gas. And so you found this yesterday in lab, hopefully, right? 2 gases at the same temperature have the same average kinetic energy. Right? When we looked at the average kinetic energy charts in lab yesterday, and hopefully you saw that for both the heavy and the light particles, those kinetic energies were about the same. The reason this is true, of course, you also saw that the heavier particles moved a little bit slower than the lighter particles. And so because the mass goes up for the heavy, the speed goes down, right? For the light ones, the mass goes down, but the speed goes up because they have to maintain the constant kinetic energy. And so no matter the size of the gas, they're going to have the same kinetic energy. Larger particles, therefore, have to move slower. Lighter particles have to move faster. All right, so this is the kinetic molecular theory for gases. Now, the main way that we use this is when we talk about gas speeds, right? We're going to use this kinetic energy information to determine the velocity or the speed of these gases. And so here we have the same gas, but at different temperatures. As we increase in temperature, that average speed increases across the temperature range, right? And so here we have this most probable speed, right? That's the top of our peak. Down here, it's, I don't know, maybe I'm going to call that 170 meters per second. At 300 Kelvin, we're there. Maybe that's 400 meters per second. At 700 Kelvin, we're out here. Maybe that's 650 meters per second. And so as temperature increases, the kinetic energy increases, and therefore the speed increases, because of course our mass is not going to increase. So speed increases with temperature. And then the other part of kinetic molecular theory talks about if we have different gases, in other words, different masses at the same temperature. Here we have a pretty heavy gas, chlorine, 71 grams per mole, nitrogen at 28, and then helium, the light guy, at 4 grams per mole. Notice that chlorine has a very slow speed here at 300 Kelvin. He's about, I don't know, 200. We already said that nitrogen is maybe about 400. Helium, man, he's way out here at about 1200. And so we saw yesterday that if you had heavy and light atoms in the same container at the same temperature and the same pressure and the same volume, then the heavier atoms traveled slower and the lighter atoms traveled faster. The lighter atoms also had more collisions per second. Heavier atoms had fewer collisions per second. We're going to look at a couple of different ways of thinking about speed. The one that we'll think about most often is the root mean square speed. And so I'm going to erase this real quick. So the root mean square kind of an odd term to think about. It's a very physicsy kind of way of thinking about things. I'm going to go backwards. So the square, that's the square root. Or sorry, the root, that's the square root. The mean is the average of the squares. So let's say that it's a squared plus b squared plus c squared. Well, if there's 3 things, I'm going to divide by 3 to get an average. And so root mean square would look something like that, right? For us, the root mean square of the speed has the symbol u, v for velocity, u for speed. So RMS, that's what root mean square. The root mean square speed is equal to the square root of 3 times RT divided by the molar mass. Our textbook uses a script M. Other places I've used MW for molecular weight, MM for molar mass. Different places use different terms, but this is the molar mass. Right here, we're interested not in volume or in pressure, but in the energy of these molecules. And so we need that other variety of R, that R of 8.314 joules per mole Kelvin. So let's do an example. Calculate the RMS speeds of helium atoms and nitrogen molecules in meters per second at 25 degrees C. So URMS, I'm just going to write that equation back out, is the square root of 3 RT over the molar mass. Let's think for just a minute about units. This R is going to be joules per mole Kelvin. A joule is a kilogram meter per second squared, kilogram meter squared per second squared. And it's joules per mole Kelvin. Right? These are the units on R. Well, we want to get speed out. What are the units that we're going to use for speed?
Seconds.
Meters per seconds.
Meters per second, that's it. So since we're taking the square root, it's okay that they're squared here. So we want to keep the meters squared per second squared. We're multiplying by temperature. And so that's going to get rid of the Kelvin. And so our molar mass here has to be in kilograms per mole. Okay. That trips students up every time we go through this. And so I just really want to emphasize that that molar mass has got to be in kilograms per mole. Right? So let's go ahead and work through helium. URMS is equal to 3 times 8.314 joules per mole Kelvin. It says 25 degrees C. That's 298 Kelvin. We're going to divide by the molar mass of helium. Helium is 4.01 grams per mole. Do we move the decimal point to the right or to the left?
Left.
To the left, that's right. So we're going to move it 3 places to the left. We're going to divide by 1,000.00401 kilograms per mole. And so we saw in the chart that this was about 1,200. Let's see how accurate that chart is. 314 times 298 divided by 0.00401. I'm going to take the square root of that. And I got 1,360 meters per second. Okay. And again, this was for helium. Take just a quick minute and do this for nitrogen. Remember, it's N2, so that's 28.01 grams per mole. All right, take just a minute and do that one.
So is this energy too?
Yeah, so because the speed of the molecules is related to the kinetic energy of those molecules, that's how we know we need to use the R value with joules in it. Again, kinetic energy is equal to 1/2 mu squared. So we're solving for that U business.
I got a really big number. Is this one like really big?
So nitrogen is a much larger molecule. So should he move faster or slower?
Slower.
Slower. Did you take the square root?
Oh, I forgot that.
And so it should be a little bit smaller. What'd you get?
515.1304.
Sure. 515 meters per second. Excellent. Okay. So being able to use those equations, again, remember to keep it in kilograms per mole. This root mean square speed is one that's used very often. There is also an average speed. I'll just throw it up here in case you have an Alex question that asks for the average. The equation is only slightly different. Instead of multiplying RT over M by 3, we multiply it by 8/3, and so it's 8 RT over 3M. Okay. And that's the average speed. So if it asks for average, use that equation. If it asks for RMS, use the 3. I'm always more interested in RMS. It's the one more commonly used, but I think maybe you might see the average on Alex. So I'll go ahead and give you that equation.
Dr. Davis,
Yes.
could you go back to the last slide and explain where the root mean square formula came from again?
So, yeah, I didn't explain it exactly. When we think about the average kinetic the average kinetic energy. Let me erase a little bit here. So kinetic energy is equal to 1/2 mu squared. It turns out that this is also equal to 3/2 RT. And so if we rearrange, we put u squared on one side. We have 3/2 divided by 1/2 is 3. And RT divided by M is M. Then we take the square root of both sides and we get U equals 3 RT over M. Okay?
Thank you.
Sure. All right. So Graham's law, gas effusion. Again, we talked about this a little bit in lab yesterday. That equation, the rate for gas 2 divided by the rate for gas 1 is equal to the square root of the ratio of the molar mass of gas 1 divided by the molar mass of gas 2. A couple people were asking questions last night in the group me, which one's gas 1, which one's gas 2? It doesn't really matter as long as you make sure that you are using the same gas for 1 and the same gas for 2. And so this has got to be a rate. And so it could be in, moles per second. yesterday it was in atoms per picosecond, right? It doesn't really matter what the unit is because divide rate by rate, the units cancel. And so we need to be sure that we pay attention to what the unit is so that we're sure they do cancel. But you'll see all kinds of different rates, usually some amount, moles, atoms, something like that, divided by a time, hours, seconds, minutes, something. Okay. All right, that's really all I want to say about Graham's law. It's a pretty straightforward kind of plug and chug equation. All right, this last bit of chapter 5 talks about deviations from ideal behavior, right? So in kinetic molecular theory, we described an ideal gas as being a point particle, not having any volume, as not having any interactions with the molecules around it, as being elastic, they don't lose any energy, and then that last bit about having the same kinetic energy. It turns out that if we take this ratio, PV over RT, for an ideal gas, for 1 mole of an ideal gas, we get exactly 1 all the way down, right? That's this blue line. However, for other gases, we get very different values depending on how that gas behaves. Most of this is due to the fact that real gases differ from ideal gases because 1, they actually have some volume, even though it's small, they do have volume, and 2, they are attracted. Attractive and repulsive forces do exist. Right. So in ideal gases, we sort of ignore these things because at low pressure, look at this pressure axis. We're up to 1200 atmospheres. Usually we're talking, we do experiments down in the less than 5 atmosphere range when everything is pretty close to 1. So ideal gases, ignoring this attraction repulsive force and ignoring this gas volume does pretty well at low pressures. But as we increase pressures, those gases start to behave differently. If this value is less than 1, then that deviation is due to attractive forces. Right? These ammonia molecules are very attracted to one another at lowish pressures. Right? If this ratio is above 1, then these are repulsive forces. Or it has to do with the volume. Right? If you think about a very high pressure, as pressure goes up, volume goes down. And so as the volume of our container goes down, there's some point at which the volume of the container is equal to the volume of the gas inside that container. And we can't get any smaller than that, right? If we do, those molecules start to crowd in and they can't overlap each other in space. And so we come to this van der Waals equation. So this is essentially the ideal gas law, but it's been rewritten for real gas. Right? And so again, think about this as P times V equals nRT. Right? The nRT part doesn't change, but the pressure and the volume pieces do. And so this corrected pressure, this corrects for attractive and repulsive forces. This corrected volume corrects for the fact that gas particles do have volume. Right? And so both of these are experimentally determined. This constant A, let me change colors. this constant A and constant B, they're in tables, right? There's A, there's B. But everything else is just like solving the ideal gas law. We just might have to put it in a couple extra places. Let's run through one quick math example here, and then I'll let you go. Ideal gas equation, I'll let you do that one on your own. The van der Waals equation, the pressure is what we're solving for. So pressure plus A is 4.17 atmospheres liters squared per mole squared times sorry, I don't know if you can hear it. I have a crying baby downstairs. Times the number of moles, 3.5 moles squared, divided by the volume, which is 5.20 liters squared, times the volume, 5.20 liters, minus the number of moles, 3.5, times B, which it tells us is 0.0371 liters per mole, equals nRT in 3.5 moles, R 0.0821 liter atmospheres per mole Kelvin. The temperature is 47 degrees C. They made that nice for us. That's an even 320 Kelvin. Okay. All right, now's where the algebra comes in. All right, I'm going to do the. It's past time. I'm sorry I ran a little bit over. Hopefully you can follow along, and you'll find out that this is this one is 16.2 atmospheres, and then for the ideal version you got 17 again. Sorry. Oh, fiddlesticks. 17.7 for the ideal version, 16 for the real version. We'll circle back and look at that example again on Monday, as well as start chapter 6. I hope you have a great weekend.
Thank you.